Hi, I'm Trish Lobline, a high school science teacher who works with the PhET project at the University of Colorado in Boulder.
And I'm Stephanie Chastain, a physicist in the Physics Education Research Group at the University of Colorado. This video is created to show how we help educators use PhET in productive ways to encourage inquiry-based activities.
Most educators immediately see the value of PhET, but don't necessarily see how they can use it in their classroom to engage students.
You'll see one workshop that we presented at a national conference as an example. This particular workshop was 3 hours long, but has been condensed to 30 minutes in the video.
There are several handouts that accompany this workshop. Please download those, as well as the slides from the workshop, which include what the presenter would be doing in the notes.
We hope you find this video useful in planning your own workshops on using PhET in the classroom. Please email us if you have any questions. We begin with a short introduction. Then we describe two of the simulations and how they are designed to promote student learning. Next, we explain how the simulations are based on research and improved through a continuous design cycle. We then give a brief introduction to designing classroom activities for use with the simulations, and we practice activity design, and give teachers plenty of time to play with the sims. We highlight the many ways that PhET has been used by teachers. We show teachers the simulation activity database. We then give participants some hands-on time to explore different simulations and find out which ones they would like to use in their classroom, before wrapping up with some concluding remarks. We begin with an introduction so that teachers know what to expect from the workshop. First, we show participants the learning goals for the workshop. These are what we're going to be talking about today, the workshop goals. We want to talk about the simulations and who we are that actually make them and how these simulations can help people learn. We're going to explore those simulations and activities. We're going to get a chance to actually play with them. But first we are going to spend about 25 minutes talking about what goes into those simulations and what they are and how they can help your students learn. And then we'll help you use them, plan to use them in your school.
A lot of people want to know who we are. We're a nonprofit. There's about 16 people that work part-time on the project. Nobody except there's one programmer that works full-time on the project. Everybody else is part-time. We add up to about like 8 people or something like that. So traditionally a sim will take about 8 months, and a design team for each sim that's made up of one university faculty who's a specialist in that field, a university researcher who's especially in education, a programmer, and a teacher who's going to use that sim. These are thanks to very much to all the people that support us. We were started by Carl Wyman when he won the Nobel Prize. He put his money toward the project.
Here's our website at phet.colorado.edu. If you click on Play with Sims, you can find over 90 interactive simulations covering introductory physics, modern physics, there's some chemistry, and a little bit of earth science and biology and math. The design of all of our simulations is based on research, and we have all information on our research on our website. We do extensive user testing on how usable they are and how users interpret what they're seeing and how they affect student learning. They're all free, and you can run any of them online. You can see you can run now online, or you can download any individual simulation locally to your computer. You can also download the entire website to your computer. If you go to How to Run Simulations and click Download the entire website, then you can run them locally on computers in your classroom. In the next part of the workshop, we talk about what features of the simulations make them effective, using 2 specific sims as examples. Energy
Skatepark is a visual representation of a real-world situation with many tools, whereas Matheson Springs is more similar to a common physics laboratory with fewer tools. And then we facilitate a discussion about how the participants perceive the sims being used in their classrooms. This simulation is called Energy Skatepark. It's one of our most popular. You can see that the students can build their own skate track and play around. The Return Skater button allows the student to make a change. Then when they press Return Skater, it goes back to the exact same place as they last put them. That way they can change one variable at a time and find out what matters. Another thing that the students really enjoy is they can change what the skater is. We've chosen some really fun things like a girl, a bulldog, a bug, and your traditional ball. There's also other tools like a measuring tape, which some students like, but we also find that showing the grid is a very popular item. A lot of students want to be able to get a context. You can always turn off the tool. Another thing is show path. When you show the path and hit pause, if you double click on one, or I guess if you click on one of the purple dots, the measurements for that particular spot are given. So that if you want a student to do quantitative analysis, it's very easy to do. So we have a pie chart that we created that follows the skater along and gives them a very interactive way to see the energy conversion. There's also bar graphs, energy position graphs, and energy time graphs. So through those multiple representations, our goal is that each student can find some way to make sense out of energy. You also can do fun things in the simulation, like go to the moon, go to Jupiter, or go to some other place where you just make your own gravity. Then there are more features down below that would be for advanced users. At this time, we usually ask the teachers how they might use this simulation with their students. This is another one of our very popular simulations called Masses and Springs. It demonstrates what a lot of people do to try to teach about kinetic and potential energy, but in a little bit different way. It has a ruler that you can move. It also has a stopwatch, but you'll see it doesn't have as many tools as Energy Skatepark. One of the things is it has some unknowns, which makes it a challenge for the students. You can ask them to find the mass of the red object. You also can change the friction of the springs. And then you can change only the softness of spring 3. So again, this simulation has a lot more constraints. The softness is what physicists would call the spring constant, but we don't use that word because we just want them to get an idea of it. Also, we show the energy graph if they'd like. And again, we don't have as many multiple representations, just that one. Sometimes the sim gets moving too fast, and so we have a way for them to slow the time down. And you can pause it and take measurements if you'd like. We also have the ability to go to other planets. And there's the unknown planet X, and you can have them try to identify what the gravity is on that one. So as you're looking at these two simulations and you're thinking about your own students, what are some things for you that would make them effective?
This is the first group discussion in the workshop. Spend about 10 minutes discussing pertinent questions, such as, what are some learning goals you can effectively address with this simulation? Are there any goals that you can address with this simulation that would be particularly hard to incorporate traditionally? And how would you use this and similar simulations in class?
So one thing here we watch for is to make sure that the teachers come up with the list of things that we know our research shows are very effective. So one thing is that they are very engaging and that there's an open style play area. You don't really have to get students very much guidance to get started. The other thing is students like it because they're very interactive. They get to play around and something happens, not at all like a worksheet. Another thing is that they get instant feedback. So when they're doing their lab, they don't have to stop and do calculations because the data is already there for them to use. Also, we make sure that there's a connection to their world. And sometimes, although it is a physics world like masses and springs, it is something real. We also make sure that we use explicit visual and conceptual models like experts use. We want to begin to help the students think like scientists. In order to do that, sometimes we had to provide constructive constraints, like low friction or no friction, or they can slow down time so that they can actually see what's going on. And another thing that we found is that although the simulations are designed with a lot of research behind them, how you use them is very important, and that's why we've developed the guidelines for use.
Now we talk about the research behind the simulation design.
One of the things about the simulations that's different is that this is all coming out of the University of Colorado's research group. They're very heavily research-based, both in terms of what we know about how students learn and also learning more about how students interact with the simulations through ongoing research and interviews on the simulations themselves. So we start out with this deep research base of what we know how students learn and how students deal with different ways of looking at information about the physical world. And we start out with what, of course, we want the students to do at the end of the simulation. What do we want them to learn from this particular simulation? So those are the learning goals. So all that goes into the initial design, the first design of the simulation. And we then improve by showing the simulation to students in interviews and watching them work through it. Did they get it? Did it make sense to them? Did they misunderstand something because of the way that we presented it? Was it easy to use? Did they interact with it? And from that, we then improve and refine the simulations. We also then bring it into the classroom and see what happens when students use it in the classroom. And through this, again, we continue to refine and redesign until we end up with something that is pretty much our final design. Although, honestly, we often come out with new versions of the simulations if there are new features or things that we want to fix about them. So that's our research process. Why does this help us to design good simulations? Well, let's give a concrete example. So this is a simulation I'm going to show you on radio waves, which is something that physicists find very exciting and interesting. It's very important for introductory physics students to understand about radio waves and how we communicate through space with electromagnetic waves. So we designed this simulation, and physicists were really excited about the simulation. You can see the electromagnetic waves propagating through space. You can see their directions changing. Experts thought that this was fantastic. You can see the electrons moving up and down, and it's creating an effect over on the right-hand side. Fantastic. But students, as you might imagine, found this really confusing. The experts liked it, but the students just looked at it. They didn't really interact with it. And they just watched it and they misinterpreted it because there was a lot going on. So we instead started with this screen with a nice big sign saying wiggle the electron. And if the student comes over and wiggles the electron, we see a wave propagating out in space. So why does that work better? Well, it matches with what we know about how people process information. The other one with all the arrows going everywhere was too much. It's called cognitive overload. And so people just looked at it and didn't feel a need to do anything to it because there's already a lot going on. Students need to construct their own understanding. Has an electron, you wiggle it, and you can figure out what's happening. Whereas when everything was already going on the previous design, there was no need for them to construct their own understanding. It also didn't call for them to be interactive. And the new one allows them to create their own models of expert understanding instead of just trying to understand something that's presented to them. So that's the way in which all of our research helps inform the simulations and improve them so that they're more effective in the classroom, and we know that students are understanding them and getting from them what we want them to.
We then explain how we suggest designing activities for use with the simulations, beginning with a demonstration of the salts and solubility simulation.
So this is one we designed. We think it's pretty friendly. You shake there, little salt molecules dissociate. The kids can play around. They can add water. They can drain the water out. And then if you want to, over here you have some quantitative data. And if they shake enough salt in. So what will happen, what should happen? Saturation. Yeah, we should get saturated. So if I keep, I haven't reached the point yet. So it gets saltier. And lots of times what I do is I demonstrate this macroscopically as well. So I start with a little 5 milliliter test tube and I throw some salt in and I stir it. And then again, so I try to tie the macroscopic and the simulation together quite a bit, just like this guy mentioned about Hot Wheel tracks. Like I do a Hot Wheel track lab and then I do a skate park lab. And so I try to mix the macroscopic. So you can see now precipitation has occurred. While I was talking, it recrystallized. And if you want to do quantitative data, if you're a chemistry teacher, you can calculate information. So this simulation, instead of in Skatepark, remember how down on this side, there just kept being more and more and more tools. This simulation, and you'll find there's basically the 3 designs. This one has tabs. So after the students are done exploring, then they move into a more difficult concept by moving to a different tab. So we have the 3 basic structures. We have the one with a lot of tools on the side, the one that you saw, the masses and springs that had few tools, and then we have these that have layered tools. Here you have slightly soluble salts as opposed to starting with table salt. The last tab is really designed for very quantitative data. You can change the KSP, you can change the cation and the anion charge. How might you use this with your students? We want to think about the physical. How are you going to get it into a lesson?
Well, one thing is it's a great way to see just through guided practice. If you've got a lab situation, you can have the kids actually put into practice what you're modeling for them to understand about a learning objective.
So you would take the kids to a computer lab and you would be present facilitating a lab, okay?
Well, and I would let them, science and math are really cool. They're just a lot of fun. And this helps the kids see that it is fun and that they can play with it and do things that mom and dad and as teachers aren't going to let them do in real life necessarily, but they could do it on the computer safely.
Okay.
What I like too about these are the variables, because in 4th grade they start in technologies, which we do science fair, and they're learning about variables. And this definitely shows them how things change when you introduce something.
Okay, so teaching about variables. Could you send this home as a homework? What a lot of people do is they don't have multiple computers and they just use them as a demonstration tool. Or like as we were talking here, if I were the instructor, I could say, what are some things we'd like to try? And you could either let a student come up here and drive, or I could drive, or you could use it as a demonstration tool. That would be another way.
I can already think of homework problems that I've assigned. They could just, when you put the grid on, I was thinking the skater one, when you put the grid on there, they could actually mimic the actual homework problem and see if their solution matches what really happens.
So he said use it as a homework to, that they could, like if they had a homework actual problem assigned, they could take the problem, do it, and then go home and test it on the sim and see if they got the same answers as the book problems. That's a really good one.
Similar to what they have on the CSAT, they're similar to what they have on the ACT. You got a picture there, here's the questions. If you change this variable, what happens? Here you can actually run it and see if what you're saying is correct.
So it'd probably be helpful to tell them this is going to match what you're going to see on standardized tests. My students are old enough that they're worried about the ACT and the SAT, and I say, you're going to see a problem like this. You're going to have to interpret this graph. One of the things we do at the university, freshman physics has 550 students, and so we use them for clicker questions. And so I'll show you some of those later.
Next, we discuss what kinds of activities best help students learn using PhET. That is, inquiry activities with minimal guidance.
How to design lessons that take advantage of the tools that are there. So what I'd like you to do is just talk to the person you're sitting near about these two lessons and spend 3 or 4 minutes thinking about teacher blue versus teacher red. And go ahead and write some of your thoughts down. You can use the back of some of our paper if you don't have paper, but I'd like you to write down some answers to these questions. What would the students perhaps learn, and what would the students be doing?
Website started with not only with collaboration between their educational faculty and their program. It started off as very
So think about that too. Think about how does the student feel about the vernacular, because that's something to think about. What we want to do is we want to compare these two questions, and you can see right away, first off, what is it? What does this mean? What does that mean? You know. So what are some things about let's start with what they would learn.
I would say that the blue teacher, or you when you were blue, blue you, would be teaching about solubility, and you might be going on then to talk about why do different salts have different solubility, where on the right you'd be more qualitatively talking about what do salts do.
Okay. So, Deborah, hear her? Okay, yeah.
Well, the blue square, we were talking, and I was looking at that, it's more directed, where it's very specific with the, there's only specific answers that kids can come up with. And it's very close-ended, which would work great on a way to guide kids on how to conduct an investigation of this sort, like an introductory lesson. But the red box is definitely total inquiry lesson learning, where the kids are learning the reactions of what would happen instead of just focusing on a single little piece.
So this question, the second question, what will they be doing? I just want to focus on what she said. What she said they would be learning in the red square. That's the verb she used, and that's not the verb she used about the blue side.
Definitely working with the overarching principle as opposed to a specific.
Okay, he said they would be working on the overarching principle. And what would it look like in the classroom? What would the students, like if you were watching your students?
Fourth graders would be saying, I don't get it. What am I supposed to be doing?
Which one? On the red. Do you think it's too open-ended? It might take some preparing them for what does inquiry act like. And so, yeah, that's something to think about.
I think on the blue side too, they're concentrating more on following the directions and working with a recipe, versus in the red, I imagine the classroom has a lot more discussion and interaction with.
Okay, she said they would be working, and there's actually in research, they call that the production mode. They would just be producing answers, versus she thought they would be visiting a lot. I forgot all the verbs you used.
Well, discussing.
Discussing.
Just, you can see a lot more interactive chatter with the one on the red.
Anything else people would like to add about that?
What I was going to say, what we talked about was, on the red side, really the only previous knowledge, prior knowledge you need is compare and contrast. Compare and contrast these salts, and just put them out there, put them in water, see how they react. The other side, I had difficulty with, first of all, how do I measure 100 silver bromide pairs? I need to have previous knowledge of how do you measure it. The other one is, vocabulary. What is soda? I need to know about that they're chemicals. So you have a lot of previous knowledge and vocabulary you have to have on the other side.
So this one has a lot of prior knowledge, a lot of intimidating vocabulary. It's quantitative right off the bat. Get to work, measure. Hear the whip? Get on it, yeah.
I was thinking about what it would look like in the classroom, and I think on the blue side, most of the groups would look similar. And I also think that they're, in my experience, kind of leaders or go-getters kind of emerge, and so you'd have some confident students doing the measuring, doing the lab, whereas, and most of the groups would look similar. And also, I can just see kids looking around to see, are we doing the same thing they are? But on the other side, it really encourages, I get to do what I want here. I get to really explore. And so I think you'd see a lot of different types of activities in the talking room.
And you teach 6th graders, right? 7th graders. So pretty young kids. Yeah.
One of the things I would do is, if I were to start with this with the middle school kids I had, all the questions they would want to ask. There's the kid that's going to go, what's a salt? What's a silver bromide? What's a pair? So the questions they ask me is, okay, we take this, we're going to set this aside. You guys have 15, however, might have to be a whole period. Say, okay, the questions you're going to ask me, you guys as a group have to go find the answers. And you come back, and in doing that, they start teaching and learning each other. Then they're using the computer, the technology to find the answers, and that takes care of some of the, you know, having to start a lesson or so before, like what's a bromide pair, what's a salt, how many salts are there. They're going and finding stuff else, or finding stuff ahead of time, so they can come back and continue this. So I would use this as an introduction to get them started.
So he's figured out a very clever way to ask this question and make them do the work, so that he doesn't have, so that he could start here if he wanted. Because he's enabled the students, he's taught them skills to help each other. So, you know, there are ways to use, you know, that question effectively.
In the next section of the workshop, we show participants our design guidelines and let them practice using them. We then hand out the blue design guidelines handout and spend about 5 minutes discussing in a group how to apply those guidelines to create an inquiry type activity like you see in the red box. The objective here is to give participants a chance to practice using those guidelines to create inquiry activities. Here are the guidelines. First, define specific learning goals. Encourage students to reason and make sense through the activity. Connect to and build on students' prior knowledge and understanding of the material. Connect to and make sense of real-world experiences. Design collaborative activities. Give only minimal directions on use of the simulations. And help students monitor their understanding by having them self-check. These guidelines were developed over many years using the research from the University of Colorado and have been shown to promote student engagement and learning using the simulations.
Okay, we don't expect that every lesson would have every piece of this. But if you strive to include some of these things in your lesson, it would be beneficial. We then hand out the green worksheet, which is a guided practice for the teachers to use the guidelines. There's 2 lessons that they can work in pairs to talk about how the guidelines were applied. Then that takes about 10 minutes. After that, we spend about 2 to 5 minutes sharing out their answers. Okay. So
We then give participants some hands-on time to explore different simulations and find out which ones they would like to use in their classroom.
now we're going to get a chance to really look at some of the simulations and think about how you might use them in your particular class. We've all got these sort of holes that we're looking to fill up in our curriculum, like some place that we know that we want some gem. So that's what we want you to think about now. What simulation do you think would be most useful in your course? But first start with thinking, what is it that you want to do in your class? And then you'll ferret out a simulation or two that will help you teach that topic. But think about why you think that that simulation would be effective for teaching that. We have a handout in your folder. It's the gold handout, which I'll show you up here. It's the sample use of PhET activities. The one we gave you is for high school. If you're not at high school, I'll show you where to find the others. But you can see that it goes through the topic areas and the different simulations that are appropriate for those different topic areas. So what we want you to do is to think about your own curriculum and work with a buddy to come up with 1 or 2 simulations at least that you think would be helpful. And
this section of the workshop allows participants to explore the simulations at their own pace. This is their first chance to really look through the website and see what matches there might be between the topics of the simulations and their curriculum. There are separate handouts for elementary, middle, and high school outlining which simulations are appropriate for which curricular areas and topics at those grades. During this time, the facilitators should circulate around the room, talking with participants and asking them about the learning goals that they have for their course. Facilitators can help participants identify which simulations are going to be particularly helpful in their class.
So can I have a volunteer to tell me something that they wanted to teach and a simulation that they found that seemed that it would help them do that? Yeah. Okay, so there are 3 main different ways to use them that you just talked about. One, using them after a real lab to sort of highlight what they saw in the real lab, using it in place of a real lab so you don't break equipment, and using it as a demonstration as well.
We sometimes show teachers some of the different ways the simulations can be used in the classroom.
That has been used in a variety of ways. You can use it for pre-class or pre-activity. We use them a lot in classes in terms of lecture for visual aids. You can also use them in labs. At the university, we use them in recitations. You can use them for group activities or individual activities. And we're beginning to study how they can best be used for homework.
So one way that we use PhET is with concept tests or clicker questions. You could do this both in a recitation instead of just solving homework problems, or we use them a lot in lectures to supplement the lecture material. So in this case, the instructor has probably showed the simulation, the Energy Skatepark, and is then asking the class a clicker question to help them work through the conceptual understanding of what they've seen in the simulation.
Another excellent way to use the Sims is to extend things that students have done in the lab. If you could use a qualitative lab like a motion probe, but the problem with that lots of times is the data is not very quantitative. Then you can use a simulation where there are controlled constraints and they can get better data. In the next slide, it shows an example of the Vernier Lab Pro, and you can see that although the students can get an idea of what's going on, they can't get very good measurements. And then there's the Moving Man simulation, which demonstrates that you can get measurable quantities.
Another thing that PhET can be used for is for inquiry labs, because PhET, unlike hands-on physical material lab, lets you easily isolate a lot of different variables and manipulate them and get immediate data in order to do replicable experiments to replace a traditional lab. So another thing that's really helpful about PhET as a lab activity is that you can do things that you couldn't do in the real lab, such as taking the skater to the moon or to Jupiter.
This slide shows one of the common demonstrations in a physics classroom is we use a piece of rope and we shake it and we ask the students, what did you see? But lots of times the students can't actually understand what they saw. So the simulation slows everything down and allows the students to see what the experts would see.
Another way that we use the PhET simulations is to demonstrate the scientific model, or how scientists understand what's going on in the world. For example, oftentimes we'll rub a balloon on a sweater and then stick it to the wall. What PhET allows us to do is demonstrate just what's happening at a microscopic level, which is that you're rubbing electrons off of the sweater and then repelling the electrons in the wall, and that's how the balloon sticks. So it makes visible the scientific model.
Another nice thing about PhET is you can change variables that you normally couldn't change. So if you had a recitation or a homework, you can give students a challenge and just ask them very open-ended questions that you wouldn't be able to do because the equipment would be so expensive. Here's an example where you want them to study lenses, and they can just play around with the lenses and find out what might happen.
Now, we show the participants the online database full of activities that teachers have submitted over the years.
Now you get down to the nitty-gritty. I want to use it in my class. I don't have time to write a lesson, or I do have time to write a lesson, whatever. We have an activity database, which I'll show you a little bit about. If you're looking for activities to use in class, you can go to the For Teachers section and go to Browse Activities. If you select a simulation and hit Browse, you can see activities that have been contributed. You can tell from whom they come. And also the ones with a gold star are those that are aligned with our guidelines that we've been practicing using throughout the workshop. You can also sort for different ways to use the Sims. So if a person thinks it makes a good homework, or if it's just a concept questions, you can find those. We also have them by grade level. New to our section is languages, but right now we don't have any contributions in any foreign language, although the simulations themselves are in different languages. Another way to find activities is to click on a simulation that you like, and then when you scroll down, there's information like the main topics, the keywords, sample learning goals, and then again you'll see activities that go with that simulation.
The white Energy Skater handouts are an example of what you would find when you download a PhET activity from the database. It has a lesson plan with some teaching tips, the student directions sheet, and clicker questions. The clicker questions in this handout cover more than the activity requires, but are included because they demonstrate a wide variety of types of clicker questions.
There are activities that we've written. There are also activities that people who have been in workshops have contributed. People who contribute to the database, the idea is that you're willing to share your information, your lesson. Anybody can download it, anybody can edit it, anybody can use it. So you will see lessons that we've written that meet the guidelines. You will see other lessons that people have just shared, and you should maybe think about the guidelines as you open up people's activities and decide whether or not they're good. One thing to be aware of, if it has a gold star on it, someone from our team has looked at it and it does meet the inquiry guidelines. If it does not have a gold star, it has not met our guidelines. But we want everybody to share, because lots of times when you look at the ones that, even if they're an inquiry, how the person used it is interesting. So lots of times I look at those anyway.
The next part of the workshop is an open-ended time, where teachers can work at their own pace, exploring simulations, looking at lesson plans, and either adapting or writing what they think is useful. Sometimes we'll ask them to develop an activity on a specific simulation, like salts or Moving Man, or they may choose their own simulation to write an activity about. They will need both the gray activity design worksheet and the yellow reflection mini sheet, both of which will help them to write their own activity. Another helpful handout is the pink Moving Man sheet, which shows a sample lesson and how it is aligned with the guidelines.
So now that you've had some time to play with the Sims and look at other people's activities and think about how you might use them in your own classroom, let's share some ways that we're going to use them.
At this point, we spend about 12 minutes having the participants share their ideas with the large group. If you have a particularly large group, say over 50 participants, you may want instead to have each pair talk about their ideas with another pair, rather than doing a whole group discussion. While each participant is sharing their ideas, we show the whole group the simulation on the large display. This way the whole group can see the simulation and understand how the participant is suggesting to use it in the classroom.
Well, thanks for all your great ideas, and it was fun to have everybody share, and really very participative. I appreciate it. I hope you get to use a sim. Please complete the feedback form. We need that. If you have ideas, contact us at phetcolorado.edu.
Since the time of this workshop, we have added additional ways to stay connected with PhET, including a blog, a Facebook page, and a Twitter feed. You can also easily sign up for our quarterly newsletter at our website. We hope this video has provided you with some helpful insights into how to facilitate your own workshop on PhET. The slides and handouts are available from our website at phet.colorado.edu/workshops. If you decide to give a workshop, please let us know, as this helps with reporting to our funders. And certainly contact us if you have any questions at phethelp@colorado.edu.